Predicting complex physics is key for science and engineering, but normal simulations can be very slow. For example, trying to actively reduce noise from a large drilling rig in real time can be a challenge. Predicting the sound spread takes many minutes for each update, often because of the heavy calculations needed for the physics. It's just too slow for immediate action. But generative models could be a real game changer here. The big question is, can they learn to make these vital predictions super fast and keep them physical correct? This led us to two core questions in our PhysicsGen paper. First, can generative models accurately learn the complex physical laws from image pairs? And second, what kind of speedups can we achieve by replacing traditional simulations with these deep learning models? To answer this, we developed PhysicsGen, a benchmark with 300,000 image pairs across three diverse physical challenges. The first task is the urban sound propagation. Here, the input to our model is the urban layout, and the target is to predict the corresponding sound propagation map, showing the decibel levels at each pixel. And the ground truth for this is generated using a noise modeling simulation framework, which adheres to the industry standards. The second task is the lens distortion. For this task, the model receives an input phase image from the CVPR25 dataset, along with specific lens distortion parameters P1 and P2. And its target is to produce the correctly distorted output image based on simulations using the Brown-Conradi distortion model. And the third task is called dynamics of movement. The input is here an image of a ball in its state t0 on an inclined plane. And the model's task is to predict the visual state of the ball at a future time tn. These dynamic scenarios were simulated using the PyMonk physics engine. We tested a wide array of AI models from units and GANs like Pix2Pix to autoencoders and several diffusion models like DDPM, Stable Diffusion, and denoising diffusion bridge models. And we trained all models consistently for a fair comparison. So what are the key takeaways? For our sound propagation tasks, the speedups are remarkable, and AI models like Pix2Pix and UNet drastically reduce prediction times from several minutes for the simulation down to just milliseconds. Accuracy-wise, while models like Pix2Pix delivered strong overall performance, we saw a clear challenge. Most architectures found it difficult to accurately predict sound in non-line-of-sight areas, especially when dealing with complex reflections. This difficulty in capturing such intricate reflection patterns points directly to a struggle with what we call higher-order physical dependencies. Essentially, while current AI models can learn basic sound spread, multipath physical interactions remain a significant challenge. Moving to the lens distortion, the key physical insight here was how the models handled the difficulty of the math describing the distortion. Our findings showed a connection when the math for a specific distortion effect was more complex due to the lens parameters. The models tended to make slightly larger prediction errors. For example, if the equation for the distortion in one direction became more complicated, errors in that direction often increased a bit. This suggests that the models are sensitive to the physical equations they are trying to learn. Finally, for the dynamics of the bouncing ball, a key physical challenge was clear when we looked at predicting the ball's up and down movement versus its side-to-side movement. Most models made larger errors when predicting the ball's vertical position compared to its horizontal position. This happens because the up and down motion during a bounce involves more complex physics and shows that current AI models find these harder to learn accurately. So to summarize our main findings, yes, generative models can learn simpler physical relations quite well, and the speedups can be quite massive. However, they largely struggle to accurately predict more complex, higher order physical behaviors. We also found that different types of models have distinct failure modes. So, for example, GANs might create plausible but incorrect states, while others might blur details or generate multiple outcomes, so kind of hallucinating multiple balls. We've made our dataset and code publicly available, so we invite you to explore PhysicsGen and help push the boundaries of physical aware AI. We are excited to share this work at the CVPR this year, and if you are attending, please come to our poster. We would love to discuss these findings with you in more detail.